Okay, so putting aside this grading scheme, so there is a little bit that I wanted to say in Fourier analysis still. Okay, so it's not that I can quickly get to the one theorem that we are going to do, but that's it's not what I want to do. I want to introduce some concepts, even if I don't get to use them much. Okay, so these are important things if you ever do this Boolean functions and stuff like this. Okay, so it's something that is useful to know. Okay, so what is it? So remember what I did last time. I just introduced some concepts, right? So we have functions on z2 to the n, which is minus 1, 1 to the n. The cardinality is 2 to the n. Then we have the Fourier coefficients. All that is general. But we introduce some special notions, discrete derivative. dj f of x is you take f at the only at the jth coordinate, you change the from 1 to minus 1 and take the difference and divide by 2. That is dj f of x. And if you want, so that somehow measures how much the jth water matters. And one way to measure that is this depends on the xi's other than xj itself. Whereas the overall influence of the jth water is the L2 norm of this dj divided by 2 to the n, L2 norm squared of djf. So that is the influence of the jth variable, and we calculated some example. Also indicated this stability question. So stability delta of f. So if f is a Boolean function, then probability that, so you start with xi's which are independent plus minus 1 votes, and suppose each of the voters changes his or her mind with the probability delta. Okay, so with probability 1 minus delta, they stick to their votes. And so you have an election with votes x1 through xn, and then you have another election next week. By then, each voter keeps his or her vote with probability 1 minus delta, and with probability delta refreshes his or her opinion. That means, again, with probability delta by 2, it can be plus 1, it can be delta by 2, it is minus 1, that is yi's. So question is, will the overall decision of the election result change if we do this? Depends on the kind of functions you're using to pool the votes. Okay, so if f is just f of x is x1, that is 1 is a dictator, then this means that only that person 1 has to change his or her vote. Of course, that happens with probability delta by 2. Whereas if it's the majority, then it is somehow that sufficient number of voters have to change their vote in the right direction. That's when it will change, etc. So that's another measure of stability of a function. These are important concepts, but there is only so much I will do in this course. Okay, so it's not that this is not a course. In these days in probability, this has become quite important. These Boolean functions and all these concepts have become important. I will introduce one more notion. It is another useful thing to know. Again, these things tend to get done only in the continuous setting, but there is no reason to do that. So here in the discrete setting, there is a semigroup. Okay, so I should say, actually, let me call it heat semigroup. Okay, so I'll explain what that is. So we are in this usual setting, z2 to the n, which we think of as minus 1, 1 to the n. So for t greater than equal to 0 and any function on this define a function qtf whose value at x is, well, the way I am going to define is I don't have to write qtf as I'll define in a way that's not entirely intuitive what this means. qtf is just you take f hat of s chi s. That is, if that is the function S itself, right? That's the Fourier expansion of the function f. But here the t enters in the following way. You would make e to the minus t times mod s. Okay. So you take the Fourier coefficients. So that is QTF is the function whose Fourier coefficients change in this way. E to the minus t times mod s times f hat of s. The Fourier coefficients decay in this fashion. Okay. Well, if so, what you'll see is that in fact it doesn't always decay. So note what is this actually? So Q0 of f. Q0 is just the identity. That is, so it is starts with the identity operator, and as t goes to infinity, what happens to QTF?
So I think Manju, if you there is 1 by root n missing in the if you want Q0
right,
of
right.
f.
So yeah, you're right. So I keep it. In the Fourier expansion, I always write 1 by 2 to the n by 2. Thanks. So that I should keep. So thanks for this. So this I always have 1 by 2 to the n by 2, right? So that I keep. So it is the Fourier coefficients which are changing. It's okay. Then this is okay. Is all right?
Yeah.
So now what happens as t goes to infinity? See, this all decays unless this is 0. So this one decays QTF hat of this goes to 0 if S is not the empty set, because then the cardinality is at least 1, and otherwise it remains. So this converges to the constant function. Okay. So what is f hat of phi? It's actually what is this actually? This is a constant times 1, where the constant is in fact f hat of phi is you take the Fourier coefficient at the empty set, which is f inner product the constant 1 divided by 2 to the n by 2. So this is 1 by 2 to the n f inner product 1, which is f of x. Is the average of f. In some sense, you start with a function f. Okay, you start with a function f, and then what happens is as time progresses, you converge to this constant function where the value everywhere is equal to the average value. Okay, so this is like heat flow. You think of f as temperatures. So the Z2 to the n is your domain. Okay, at each point there is a temperature to start with that is indicated by f of x. And as time progresses, heat flows from higher to lower levels, and ultimately everywhere the heat will get equalized. And that is the way you think of this. Okay. In fact, I will make that more precise. But what is this semigroup business? Semigroup is the following, that Qt plus S. So this is one property that we see. And then we also notice that Q T plus S is Qt compose Qs. This is why it is called a semigroup. Okay, because what happens if you apply Qt compose Qs f? Okay, so what is the Fourier transform of this at a subset capital S? Okay, so this is small s, this is capital S. Okay, so sorry for yeah, maybe I make it like this. So by definition, Qt, when you apply to a function QSF and take Fourier transform, it is e to the minus T times the cardinality of S times QS F hat of that S, which is e to the minus T times the cardinality of S, and this is e to the minus smallest times the cardinality of S times F hat of S, which is e to the minus T plus S times cardinality of S, F hat of S, which is what QT plus S does. So these are two functions whose Fourier coefficients are this, so they are the same. Hence, so this is a semigroup property. So that is, so every time, what is semigroup? It occurs all the time in physics. I mean, in the sense, anytime you think of a system evolving, let's say you have some k planets which are attracting each other by gravity and whatever other forces, and then they evolve. So semigroup is what usually tells you what happens after time t. If it takes a current state and tells you what happens after time t. So it has this property that if you take time t and then go on for another time s, it's the same as if you start here and go for time t plus s. So that is the semigroup property. Okay. So why, I mean, what is heat about it? So this is the semigroup. I talked about the heat business. So that is seen in the following way. If you want to understand, this is a very, very important operator. This operators are extremely important. Again, our use of them will be very limited, but I want to introduce the concepts. And these things occur in continuum setting where there are more technicalities many a time, but here it is easy actually. So one way to look at what is this heat equation is look at what happens to this. Let's look at qt f of x and take the time derivative of that. Okay, so what is it? It is d by dt. Qt f of x is just the sum over all subsets of n, f hat of s, e to the minus t times the cardinality of s, chi s of x. Now what happens when you differentiate that? You differentiate this e to the minus t mod s, right? So you get minus okay, you get something like this. Now, what is this actually? So, what is this quantity? So, this quantity is, well, we can write it in the following way. I mean, I'll just write it in the following way. So, the cardinality of S is there, right? So, it's almost like the formula for Qt, except that there is a cardinality of S. So, what we can write it is, let's write like this, sum over S contained in N, sum over J that belong to S of f hat of s e to the minus t mod s, and I will write it as xj times chi s minus j of x. Right. So what happened here? So this cardinality of s. So by taking counting instead of writing cardinality of s, I do it for each j in s. So each of these terms will come exactly the cardinality of s times. So that is okay. And I also did chi s of x is the product of xi over I in s. I have written it as product of xj and the remaining. So that's what I did, which if you see, if I interchange the sums, will look like this. J in n, so over all j, I get xj times, okay, xj times sum over s contained in n of f hat of s e to the minus t mod s uh, okay. So is that okay? I just interchange the sums and sum over j first and sum over all s, but s containing j. Sorry. Only those s which contain j, we sum this. Now, if you see, this is actually, we can now write this in terms of the differentiation operators. So this whole quantity here, this thing is actually d sub j applied to qtf of x. So qtf of x is this expansion, right? So qtf of x is basically this. What happens if I differentiate with respect to the jth variable? You only get subsets which contain j, and in each of them xj will go away, right? So this is actually minus summation xj dj qtf of x, which we can write as, we will write as minus L qt f of x, where just I introduced this new thing. L is xj d sub j. Okay, that means it acts on functions like this. Lf of x is so this thing is, it looks like, what is the, if you remember the heat equation. So let me just write here. What is heat equation? Is that d by dt u of t ut, I mean, if you want ut of x, so instead of writing, let's write ut of x. The usual heat equation looks like this. Sometimes there is a factor of 1/2. Should I put that in here also? Let me just see my this one. No, I don't put it. Okay. Sometimes it's common to put a factor of half or not. It doesn't matter. So this is the usual heat equation, where this is the Laplacian. Which is if depends on the dimension in which you are doing the equation. So this is the heat equation, right? So it is a differential operator. So this Laplacian is this summation of the second partial derivatives with respect to xi's, and this is the time derivative. Earlier in the very beginning, I gave example. I gave it in one dimension. So you had time derivative on one side and second derivative on the other side. But in general, it is the sum of the second partial derivatives. That's the Laplacian. Now you see the similarity to this. So here d by dt qt of f is giving some differential operator L times qt f of x, and this L is taking the place of the Laplacian. So we'll call this the Laplacian actually. So this is the Laplacian. Okay. So that is so in that sense it is like the heat equation. But in what sense is this like Laplacian? I mean, if you is this okay? Is there any questions? If you have never seen heat equation, it may not provide much of a motivation, so to speak. But otherwise, it might give the analogy here.
I think, is there a normalization thing? Is there a 2 or 1/2? You mentioned this, but
Sorry, again I did something that I forgot. Okay, I forgot this 2 to the 1 by n, 2 to the minus n by 2 here, right? I mean, so what you said earlier. So I should have put 2 to the n by 2. 1 second. Here in all this, right? Because that's what there is there in the Fourier expansion, 2 to the n by 2. But then finally, when I come back to this, that gets absorbed back. Here.
no, but the DJ operator, that's the same DJ you used before, right? Just put jth variable as 1 and minus 1 and subtract and then take divide by 2.
Right. And you know that DJ, how it acts. Okay. Yeah, exactly. That's what it is.
Yeah, but then where is that factor half in that? When you write DJ.
Oh, okay. So there is no factor half because chi s changes by. Okay, let me see. Did I do it or not? 1 second. So DJ. So I defined this operator DJ f of x is what you get by taking f with 1 in the jth coordinate with minus 1 in the jth coordinate. Take difference, divide by 2. Now what happens when I apply it to the chi s of x? Okay, so if you
Okay.
yeah, it changes by 2. It changes from
Yeah.
So it is chi s slash j without any such thing. So because of this, maybe I didn't write here. Maybe it's a place I can write here. Because of this, you can think of here is one way to do the differentiation. If f is chi s, okay, then dj is a linear operator, right? It is very clear dj by definition is a linear operator. So you can apply it here. So you apply it to each of these chi's. So it is 1 by 2 to the n by 2 sum over s, but only those s that contain j, because otherwise this will become 0. F hat of s times chi s slash j. Okay, so you can just differentiate like this. So this is how dj acts on a function. It all those s which contain j, they get differentiated. The rest will just get 0, become 0, and this is what you get. Is this okay?
Yeah, thanks.
This is what I have done here. So this whole thing, sum over s containing j, f hat of s, this is the Fourier coefficients of QTF. Therefore, this is dj QT of f. Any other questions? So this is the Laplace. So why do I call it Laplacian? I mean, is Laplacian, does it have any meaning? Okay, that also has meaning actually. So if you see, what does this L do? This is a little bit to a question that Kaushik raised last time. I will come to this. What does L do? Let's look at L. So apply it to some function. Just to avoid confusion, let me just say LG. LG of x is summation xj dj g of x over j equals 1 up to n, right? By definition, L is nothing but summation xj times dj. So you take xj dj g of x. Now what is dj g of x? Is g of x1 up to xj minus 1. Let me just write d1 for simplicity. It's just. So let's take d1. d1 g of x is g of 1 x2 to xn minus g of minus 1 x2 to xn whole divided by 2. So let's multiply it by x1. So then I get times x1. What is this? There are two possibilities. It is x1 is 1, in which case this is g of 1 x2 to xn minus g of 1, g of minus 1 here. X2 to xn by 2. If x1 is 1. And if x1 is minus 1, this will get flipped. It is g of minus 1 x2 to xn minus g of 1 x2 to xn by 2. If x1 is minus 1, right? So Kaushik asked last time, this derivative didn't depend on xj itself. If you want it to depend on xj, you can multiply by this xj itself. So then it will depend on xj in this way. So what is this? We can write it in a unified way like this as 1/2 of g of x. Let me introduce some notation here. X dagger 1, x this wedge 1. Sorry, it is g of x minus x wedge 1 is the one with coordinates. Its coordinates are same as xj, except the jth xj for j not equal to 1, and there you flip the coordinate. Okay, so this is g of x minus g of the x with the first coordinate flipped, right? So that's how we write it. Is that okay? That this is what this is. So xj times d1 dx1, this I have done for 1, but that's the same for any coordinate, right? So what we have here can be written as 1/2 j equals 1 up to n g of x minus g of x wedge j. X wedge j means in the jth coordinate there is a flip. Others stay. Others stay safe. So this is, what is this? This is actually, if you think about it, this is actually g of x minus g of xj. So let's write it in the case n equal to 3. Okay, when n equal to 3, you can indicate the z2 to the n as points of the cube. This is -1, -1, -1. Maybe this is 1, -1, -1, etc. Right? And here is 1, 1, 1. So what Lg of x is doing is, you suppose this is Lg of x. I mean, suppose this is x. What is Lg of x? It is saying that you take g of x minus all the neighbors. What are neighbors? This is a graph where neighbors are those you get by flipping one coordinate. Okay, so if you flip the first coordinate, you will go in this direction. If you flip the second coordinate, you will go in this direction. If you flip the third coordinate, you will go in this direction. So what you are doing is you are taking the values at the three neighbors, the difference from the value at the point itself, and you can average or you can just add up. Okay, so this is taking the, in some sense, the difference between the average of the neighbors and the value at this point itself. Okay, so Lg of x is so is a multiple of fx minus the average of f at neighbors. At neighbors of x. So it's like, that is what Laplacian does. it takes the value at a point and subtracts the average of the value at the neighbors. Okay, I will explain that point maybe slightly. But this is what is in general, what is the neighbors? You will take the Hamming cube. So these neighbors are in the Hamming cube. For general n, we have this Hamming cube, which is basically Z2 to the n, and x and y are neighbors. If they differ in a single coordinate.
Manju, was there a negative sign in L somewhere?
Yeah, I don't know whether I should have put the L into this. Or I have a minus hanging out here. I actually, it is possible that overall I have made a sign mistake. It's a very likely thing. So sometimes Laplacian is defined with the neighbors minus the function. So both are used everywhere. I mean, not everywhere. In both L and there's no uniform convention whether this should be taken with minus or plus. I mean, both in discrete and continuum setting. I may have made a mistake in sign somewhere though. Okay, but modulo that it's okay. So this somehow measures the, this is what is called the Laplacian. Even the continuum Laplacian is actually measuring this. We have defined it with second derivatives here, but what is that? It is actually, it is something very similar. I will explain here. So if you have ever seen Green's theorem and so on, so you may know the following, that Laplacian f of x is actually the limit as r goes to 0 of, you take the ball of the sphere of radius r around x and average take f of y minus f of x. And average it over the sphere of radius r with respect to the surface area. So you think of 3 dimensions. You take a point x and you want Laplacian f of x. You take x plus a ball of radius r around that point, a sphere of radius r, take value of fy minus fx at the center, and then average that over that sphere, and then but you have to let r go to 0 also. And then there is an overall constant, which I don't remember. CD will have some pi and d and such things. We don't, maybe volume of the unit ball or something like that. We don't care. So, but this one looks very similar to this, right? So this is just to say this looks similar to this, except you have to let r go to 0 there. So this is why this is called Laplacian. So the analogy between this and the heat equation is very close. Okay, very close. So this is an important semigroup. Any questions here?
Sir.
Yes.
Sorry, simple question. Semigroup, because is there no inverse? Is that why it's a semigroup?
Semigroup, yeah, you may say that way. I mean, so Q minus T is not well defined. So QT, you can compose these things. So semigroup is something where you can multiply 2 elements. So all these QTs together form a semigroup. In fact, they form a semigroup isomorphic to R plus. R plus under multiplication is a semigroup. You can multiply 2 things. You get another positive number. R plus is 0 infinity. But you can't find inverses. So that's same with QTs. QT compose QA. QT multiplication is this QT into QS. That will give you QT plus S. But inverse is not there. That's why it is called a semigroup.
Thanks.
Isn't it isomorphic to R plus with addition? Because Q0 is. Wait a second. No, you're right.
Sorry. Yeah, you're right. R plus, with plus. Sorry, QT compose QS is QT plus S.
Yeah,
so T and S give you T plus S, not multiplication, addition. Thank you.
And also, what is the problem with negative numbers? Suppose I take q of -1 or something? Is there something
Well,
that goes?
at least I can't write as exponential of something.
Okay.
So here for any t positive, e to the minus t mod s is actually positive. So this has many nice properties. It's possible to extend qt. I mean, so in Ryan O'Donnell's book, he also defines, I shouldn't call it qt, but so to speak, this e to the minus t is replaced by a negative number. You can do that. Instead of writing it with parameter t, if I took e to the minus t as the parameter, let's call it alpha, then I have alpha to the size of s. I can also, that alpha is between 0 and 1. But you can let that alpha also in -1 to 0. It's possible.
Okay.
Yeah, that's possible. Any other questions, comments, and so on?
Sir,
Yeah.
also this expression, the QTF, that looks like very similar to the Laplace transform itself, where we take inner product against e to the a plus j omega, unlike e to the j omega in the Fourier case.
This is not, yeah, I mean, yeah, yes, the similarity is there somewhat, but yeah, should I say Laplace transform? Okay, I don't know. Maybe you're right. No, it is no. Sorry, no. It's not analogous to Laplace transform. In Laplace transform, you will average against exponentials, right? So here you fix t and you're just taking this. It's not. It's so if you're thinking of Laplace transform, you take a function, multiply it by e to the minus tx, and integrate over t. Or integrate over x. Sorry. So okay, I don't know whether to call it analogous. Yeah, I don't know what to say. Maybe it is yeah. Any other questions, comments? So this Q also has a probabilistic interpretation, but I think it may be a little heavy now if I pile that on. So let me just leave an exercise which is there in the notes. Let me not talk about the probability interpretation of this QT at the moment. Instead, when I come to it later, let me come to it. Okay. So another nice property. Okay, one more nice property of this QT is. So maybe I'll put that all as exercises. Other nice properties is if f is a non-negative function, then QTF is a non-negative function. So non-negative functions stay non-negative. In some sense, this makes sense if you think of the heat thing. If at time 0 you started with positive temperature everywhere, heat will flow from hotter to colder regions, but nowhere should it become negative, right? Well, that's a very heuristic, but so you can prove this by the definition. QTF stays. You see, one of the things I did remark on this earlier is that properties. So one reason why Fourier transform is very useful is that properties of the function and properties of Fourier what are some things that are not obvious about a function become obvious when you go to the Fourier side, in the Fourier transform. But that also means that some things that were obvious earlier will become non-obvious. It has to be. If not, then this type of duality is not useful. This duality is useful because you have completely different view of the same object from a different direction in some sense. When you go to Fourier transform, certain other properties become obvious. Properties which are obvious will become non-obvious. For example, you give me a function, okay, on any group, okay, whether it's positive or not is a natural property you can see from the function. If you go to the Fourier side, if I give you all the Fourier coefficients and ask, is the function a positive function, it is completely not obvious actually. Because Fourier coefficients are averages of function with respect to some complex valued functions. It's you cannot at all see that property. So positivity is one property which becomes non-obvious on the Fourier side, and my definition of Qt was using Fourier. So you may have to think a little bit how you will see this property. Okay. Anyway, I will leave that. Another thing is which I want to mention is, yeah, what was that other thing I wanted to mention? I completely forgot.
Sorry, one question, and maybe this is where you're going anyway. You mentioned this heat sort of settles everywhere, which sounds like a stationary distribution.
Right. So that is the Markov chain interpretation,
okay.
which I did not give.
Okay, thanks.
I don't know how comfortable people are with probability. If people are comfortable with basic probability, nothing much, then I can mention that also. But okay, that was not clear to me, so that's why I didn't mention that. But here in exercises, there was something else I wanted to give. So this is what I wanted to give. So show that when you look at it as an operator from LP to LP, the norm is 1. For all p in 1 to infinity, both included. Okay, so let me tell the trivial case. So when p is 2, QTF, 2 norm squared is, by definition, I mean, by Plancherel, it is 1 by 2 to the n. The Fourier coefficients are f hat of s times e to the minus mod s, right? E to the, so you will get this one. Now, this is because this is always less than equal to 1. This is 1 by 2 to the n f hat of s squared, which is the L2 norm squared of f. Okay. So that's the privilege of teaching the course. You get to do the simplest case and leave the others to as exercise. Okay, so this is clear. For also Qt, I mean, equal to 1, because that you don't have to worry. It's really this type of thing you have to do for general LP. Okay, so one thing which is very clear is Qt applied to the constant function 1 is 1 for all t. If you take the constant function 1, what happens is all the Fourier coefficients are 0 except the empty set, right? So, and that will stay as it is. So Qt of the constant function will be constant function, which also makes sense from the heat interpretation. If you start with equal temperatures, there is no heat flow anywhere. So that is what this is. So, but now I am asking you to show that from P to P, it is actually a contraction. That is QTF LP norm is less than equal to LP norm of F. That's an exercise. Okay. So now what? I mean, so yeah, so let me leave aside the Markov chain. So should I go to the voting business or tell the Markov chain interpretation? I'm thinking. So one great thing that will come later is the slight improvement of this. That will be an important thing. But this one, do the exercise from definition and a little bit more. Okay, so just do this. It's a nice exercise. Okay. Yeah, so if I give the probability interpretation now, then I won't have time for the voting business today. So I will have to start that Wednesday. Should I do that? Yeah, what is the general thing about probability? Are people comfortable with Markov chains? Do people know what a Markov chain is? Is there anybody who does not know what a Markov chain is? Anybody who does not know what Markov chain is? No one? Okay, in that case, let me tell you the Markov chain interpretation of this. Okay, so it's something that you are safe to say, you may safely ignore also. It's okay. So, but that is where this comes actually. That is another useful Markov chain. Markov chain interpretation of Qt. Okay. What is it? By the way, another small exercise was there. So actually, which I forgot. Okay. Anyway, it will come. It will maybe after this Markov chain interpretation, I can tell it. So how you interpret this is Markov chain terms is like this. So you take Z2 to the n. Okay. So these are points of Z2 to the n. So I'm just writing them on a line. Okay. That doesn't mean anything. Okay. So this is some x. I mean, or rather, yeah, x is an element of Z2 to the n. Okay. Oh, sorry. What am I doing? No. Sorry. Sorry. So I write 1 to n. Okay. So these are coordinates 1, 2 up to n. These are the so to speak coordinates of vector. So at time t equal to 0, we start with some x1, x2, x3, xn, which we can call as x. As a vector, it is an element of z2 to the n. Okay, so that is each xi is plus or minus 1. Now what happens is like this. So how does the Markov chain evolve? At time t equal to, this is a Markov chain in continuous time. Okay, so time goes like this. So at each coordinate there is a line. Okay, so timeline. Okay, so on which there are these marked times. These are random. I will explain in what way they are random. Like this. Okay, above each k in 1 up to n, we have a what is called a Poisson process. It's nothing very sophisticated. I mean, if you know exponential random variable, it is this. Poisson process is a sequence tk1, tk2, tk3, a sequence of times. Okay. So for example, this is t 3, 1, this is t 3, 2, and so on. This is t n, 1, t n, 2, t n, 3, and so on. Okay, so what are these tks? tk1, what is the meaning of this being Poisson process? It means that the interval times, so the times between them, these are IID exponential. IID exponential random variables with mean 1. Okay, so the mean 1. So as I say, if you are not familiar with Markov chains, you can ignore this entire thing. It will be all right. Okay, so don't let this derail anything else. But for those who understand, here is the nice interpretation. So is this setting clear now? So we start with this 1 to n. Above each of these points, there is a timeline. Okay, the same timeline you may say, but there is a clock which rings at these times. Over time k, there is a clock k which rings at time tk1, tk2, tk3, and so on. Over each k, there is a different clock, and they are all independent of each other and everything. So what is the Markov chain? So the Markov chain is like this. Markov chain has state space Z2 to the N. So that means at any time and continuous time. So what happens at time t? At time tkj, okay, or tkr, the kth coordinate flips, let's say. Should I say flips or refreshes? I'm thinking which is the maybe refreshes. I mean, this will only make a change of half, one of the two. Okay, I have to figure out, maybe it is not flips, maybe it is refresh. Meaning, so at the beginning, let's say you start with all plus ones. First thing at time tn1, this one refreshes, meaning it will randomly be set to +1 or -1. And then as time progresses, the other coordinates remain the same. And as time progresses, when this time comes, so that is at this time, the first coordinate will refresh, be set to +1 or -1. At this time, the second coordinate will be refreshed. At this time, the third coordinate is refreshed. At this time, the second coordinate is again refreshed, and so on. So this way, the Markov chain evolves. So xt is the configuration at time t. So xt belongs to Z2 to the N. So this is our Markov chain. So if you have never seen continuous time Markov chains before, it is just like discrete time Markov chains, except that these times when the flips happen at random times, and you may not quite see why I took exponential one. I could also have taken some other IID times where the flip happens. But then you lose the Markov property. If you have to keep Markov property, the memoryless property of exponential is very important. And so it so happens that if I tell you if I slice at a given time, and I tell you what are the configurations, whether this is +1 or -1, this is +1 or -1, this is +1 or -1, and so on, then the future evolution is not affected by whatever happened before. That Markov property requires you to make this as IID exponential. If you put IID uniform, that won't work. So that's how this is. Now, what does all this, any questions about this description? I haven't yet related it to Qt. Is there any question? Okay, so now the relationship to Qt is this. Then I will just state it, and if you know all this, then it is easy to do this. If you are not familiar with Markov chains, completely ignore this point. Qtf of x is nothing but ex f of xt. Okay, so let's understand what this means. This means that you start with x. Suppose your starting is some x1, x2, xn, some little x1, x2, xn, and you run this Markov chain up to time t and look at what you get. That is a random thing, x sub t. So you take the expected value of the function at that point. That gives you as a function of the starting point. For different starting points, this expected value will be different, right? So for example, think of time t equal to 0. When time t equal to 0, this is just x itself, because at time t equal to 0, the chain is at x. So qt f of x will be f of x. That's identity operator. Okay, so that's what it is. So this is what the relationship between this qt, which I indicated here, and Markov chains is. Okay, so yeah, so for those who know the words, this L will turn out to be the L or minus L will be the generator of this Markov chain. It is the infinitesimal description of how the Markov chain evolves. Yeah, but let me not go further into that. But Markov chain interpretation is useful. For example, look at this question. If f is positive, QTF is positive. Is obvious from here, right? From Fourier definition, it's not clear. From Markov chain interpretation, this is clear because if f is a non-negative function, its expectation will also be non-negative. So QTF of x will be positive. I mean, non-negative. So some things are clear from Markov chain interpretation. And also what happens, it is also telling you what happens. So at time t equal to 0, it is fine. As time progresses, the xt, the Markov chain, forgets the initial configuration where it started. So as time goes to infinity, this becomes independent of what happens. And so you just get the expected value of f. In the end, like here, QTF will converge to the constant where C is the average of f. So etc. etc.
It's 1 o'clock.
Okay, so I didn't do anything else, but okay, so this is about the semigroup and the heat interpretation. Okay, so one important exercise, please do this exercise, especially those who are crediting. This is a nice exercise, QT, P to P. If you don't get it, you can ask me for hints. Okay, it should be, you probably will get it. Okay, I will stop here, but any questions, comments, etc., I'm happy to take.
The second exercise,